we move on and we stick with the topic of SPE. And now it's really important, if you would like to bring the data to the last mile of the field, you need to bring a certain percentage of power there as well to keep the sensors and so on running. So I'm really happy to hear something about power over SPE, challenges and solutions right now. And I'm even more happy to have Michael Brichter with us. You should see him. Yeah, I see him. Hello, Michael, can you hear me?
So apologies for everybody with the technical difficulties, because as you can see, I'm dialing in remotely. I'm dialing in from Ireland. So we are going to talk about single pair power over Ethernet. That's the focus of today. My name is Michael Brichter. I'm with Analog Devices. I'm a system applications engineer for industrial communications and control. And I have interesting topics for you today. So we will introduce the single pair over Ethernet, single power over Ethernet. And then I would like to talk about factory and building control applications and the single pair Ethernet in that context, with the reliable plug and play features that are there. I'll dive a little bit into the power coupling circuits, and then briefly mention process control applications where the power is a little bit different with different requirements, and then wrap up with some analog devices. What product solutions do we have on offer? So first, a little bit of introduction. Where do we see the SPE application, and the same for the power for these applications? So the idea is, over the same cable you can take power from the device controller and power another device. So the source of the power will be typically switches or controllers, and the devices that will be enjoying the power will be something like elevator panels in the buildings, thermostats, different sensors in the process or in the factory applications. So single pair power over Ethernet, the SPOE shortcut. You may have also heard power over data line, POODLE. The SPOE is becoming more the IEEE term for the SPE for industrial buildings and other applications. And there is a standardization about what power at what voltage should be delivered from the power source to the power device. So some terminology: power source equipment is the device that is giving the power over the cable. The power device is the device that is taking the power and using the power for its own operation. And as you can see, it's sharing the same cable. So by principle, over single pair Ethernet, it's quite simple. It's AC coupling of the data, AC coupling of the signal covering the data, and DC coupling usually through inductors of the power itself. And then we can see different standards. There is IEEE standard, and I will talk more about that, and also APL, Advanced Physical Layer Port Profile standard for the process control applications. Start with the factory and buildings. So as you can see, the power classes, these are defined in IEEE for different devices that need different power, starting from over a watt, going all the way up to over 50 watts of power over the single pair Ethernet. And you can see two different voltages. And I'll talk a little bit more about that, because some devices may need 24 volts for various reasons. One reason is, especially in factory, 24 volt is a very common low voltage power supply for pretty much everything, for PLC, for actuators, and so on. Also, in some environment, like wet environment, 24 volt is the safe voltage. So you can't go much above 24 volts for a safe operation in wet environments. But then there is advantage of using high voltages as well, and I'll show you on the next slide. If we use 24 volts and use an example of 25 ohm resistance of the cable, depending on the cable thickness, on the gauge of the cable, we can go 1,000 meter, and the 1,000 meter is really limited by the standard. You can go probably longer distance. So at 24 volts over this cable example, we can deliver 3 watts of power per the IEEE specification. Now, if we increase the voltage to 55 volts, over the same cable, same conditions, we can almost quadruple the power, 20 watts. So that comes from physics, and that's why the standard enables both voltages, one for safer operation or more standard factory voltage operation, and the higher voltage for delivering higher power levels. Now, the challenge, of course, comes if you want to have a plug-and-play system. We can't afford to connect device that is built only for 24 volts. If we connect it to 55 volts system, we would risk damaging something in the 24 volts device. And that is the reason for the classification. That is the reason why there are different power classes, and the different power classes operate with different voltage. And I'll show a little circuit here. So it's using some integrated circuits and some discrete components around it. So on the left-hand side is the device delivering the power. On the right-hand side is device taking the power. But there is a communication, there is a serial communication classification protocol against standardized in IEEE that makes these two devices talk, and they talk before they turn on the power. So at the start, the device on the left-hand side delivers only trickle power, something like 5-6 volts power with very limited current, and looks for a device to be plugged in. And if there is another device plugged in and the device is ready to take the power, they communicate to each other through that SCCP, through that serial communication classification protocol, and they agree if they are compatible. If the device on the right-hand side can take the voltage that the device on the left-hand side can offer, and only if they are compatible and the operation is deemed safe, then the power is turned on. So just to give you a glimpse how the SCCP looks like. So it's a relatively low frequency, single wire serial type communication. The whole classification takes about 200 milliseconds after you plug in the device. And through this principle, it's really plug and play system. You can connect any device to the cable that is delivering data and power, and only if the operation is safe, they will connect and turn on the power. And then the controlling device on both sides, the PSC controller and the PD controller, they also ensure the safe system operation. So they ensure that the power up is smooth. So it's slow ramp up of the voltage, controlling how much current is flowing, checking how long does take on the power on. And also on the power device, it is only turning on the rest of the circuitry again when the appropriate power is available. And of course, it enables monitoring the current and voltage during the whole operation of the system, and provides short circuit protection and other safety measures. So that's a PSC and PD controller. Now a little bit about power coupling, because that's a question that we've been asked as, we provide the PHY and other devices for the SPE system. So as I said, there is an AC coupling, usually with capacitors of the data. So the data come from the cable or go to the cable through AC coupling between from the PHY physical layer device that communicates the data, and through an inductor, it's connecting the power. Again, either taking the power into device or delivering into the cable. So capacitive coupling, pure capacitive coupling is one of the options. But of course, if somebody needs a better performance, they can use transformer. You can use transformer for the same SPE. You probably will still, not probably, you still need capacitors to block the DC current flowing through the transformer. But the transformer now can provide galvanic isolation, can provide more robustness against common mode voltage disturbance. And the power can be delivered isolated or non-isolated, depending on the requirement on the end system. And this is a version with 2 capacitors. We can also show version with single capacitor connected in the middle of the transformer. And again, I'm covering this topic because that's one of the questions that I'm quite often being asked, how to couple the data and power. Now, if we look at the power, there's quite a lot of inductors. So there's transformer, there is optional common mode choke, but mainly we will look at the power coupling inductor because that's the inductor that is carrying the whole power. So because the inductor is here differential, the current is flowing through both windings and it's saturating the magnetic core, the inductor has to be appropriately sized for the level of power that it's supposed to deliver. So let's have a look at the inductors. So an example, and you can see size about 12.5, 8.5 millimeters. So that's the size of the inductor. And then the inductor needs to have a certain inductance. And it needs inductance because it needs to block the communication signal from disappearing into the power system. So it needs certain inductance, 2 times 220 microhenry, and it's coming from physics. The two inductors, if they are sitting on the same magnetic core, has actually square times the total inductance. And the inductance, the level of inductance can be seen and can be tested. One of the tests required for the SP communication is a droop test. So the droop specification in IEEE requires that the droop, which means how much, if you connect, if you make a pulse, how much is that pulse decaying over time? And there is a specification, and over specified time taken in specified points, the droop needs to be within 10%. So as you can see, 220 microhenry inductance would fulfill the 10% requirement and can deliver in this size of inductor power about 20 watts. Now, if we lower the inductance, and one more, there is also return loss specification. So same inductor, and there again is a IEEE specification for return loss. There are methods how to measure it. And the return loss limit, and the inductor is below that limit, which means complying with the standard. Now, if we lower the inductance, we can, on the same core, the same size, we can go much higher power. We can go up to those 50 watts on the same core when we lower the inductance. But then if we lower the inductance, you can see that we have much more droop. Because the inductance is lower, the inductor is charging, is building its magnetic field, and eventually it will just conduct everything. So with this inductor, 30 times microhenry, again, 2 of them on the same common core, we can see 25% droop. So that's violating the original IEEE specification. And the same if we look at the return loss specification, that inductor at low frequency would violate the return loss specification. So there is a trade-off between the inductance, which is related to the size of the inductor, physical size, how much space does it take in the application, and the power it can deliver. And because we saw that challenge, we as Analog Devices, through participation in IEEE, there is an amendment to the specification that came out late last year, and it changes the specification of the it changes some of the specifications in the IEEE. It changes the droop specification, and it changes the return loss specification for the specific case when there is a power used in the system, and that enables to use a smaller inductor for the same power, or the same inductor delivering more power in the system. So I wanted to address this topic a little bit in detail, and then As analog devices, we provide you solutions. So our main business is the chips. So we provide the SPE controller and PD controller in form of the chips, and that's what we hope and recommend to use for this plug and play power over Ethernet, single pair power over Ethernet. And we also have evaluation system. So it comes with a graphical user interface. You can see there is the motherboard. For the PSE controller, it has 5 channels, so you can plug in 5 modules for data and power coupling. And by default, it serves the 10 base T1L data, but it can the PSC and PD controller would work with any single pair technology up to gigabit. Then I wanted to briefly mention process control applications because the power requirements there are different. And it's engineering, I would call it engineering power for explosive and intrinsic safety. So if we look at the application, process control, traditional wired with 4 to 20 milliamp loops, now migrating to more modern and delivering much more data to the end nodes through the single pair Ethernet. And I've spoken about that and my colleagues on this forum for many times. But now let's have a look at the system from the power point of view. So the paramount in the process control is explosive and intrinsic safety. And just to give you some examples, so it could be hydrogen plant, it could be petrochemical plant, it could be any chemical plant. It could be a flour mill because the flour whirling in the air is also highly combustive and could explode. So any of these environments where it's a danger of explosion, they need to be very, very controlled how much power and how to deliver power in these systems. So there is a specification that today is called APL, Advanced Physical Layer. It will make it to a standard, to IEC standard. And it defines the topology. So they talk about trunk sitting in the safe environment and spools going to the dangerous environment. And there are specific power classes for that. So if the device is to sit in the most dangerous environment and be protected against explosion by intrinsic safety, which means there are other means of explosive safety. You can hermetically seal it, fill the whole device with nitrogen and make it safe that way. But if the device is going to be intrinsic safe, which means safe by limitation of power that is in the device, there's a power class C, which is about half a watt of power. So again, these systems are made to be intrinsically safe. So there cannot be just plug and play and yeah, let's have a look. If this device needs 20 watts, 50 watts, can the system deliver 50 watts? That does not work in this environment because it needs to be intrinsically safe. So the power classes are fixed and there is a very tight regulation how the cables are connected and so on. So that's a different level of power over Ethernet, but still it is single pair power over Ethernet and belongs to that category. And the challenges there in the device design is the protection. So if we take half a watt, it's half a watt working. It can be up to 5 watts in case the intrinsic safe barrier in the switch has failed. So there's lots and lots of design challenges. And we can assure we understand the challenges. One of the things is 1 volt peak to peak amplitude, which is one of the 10 base T1L recognized standards amplitude. The amplitude is there not because the 2.4 volt amplitude will break the power budget, but because all these components, power coupling inductors, need protection, double, triple protection. And those clamping devices work easier. It's easier to design them when the amplitude is limited to 1 volt peak to peak. So again, we understand the challenges and we can help you with that. We have evaluation boards for the 10 base T1L single pair Ethernet. And that evaluation board can take plug-in modules for playing with the power, with the magnetics, specifically with that engineered power. And you can see different magnetics from different vendors, and we can combine and we can play with them. Only power delivery, no common mode inductor, common inductor transformer. You can, if you want to start with single pair Ethernet and play with the power at engineered level, that's the tool that you can have from us. It's available on our web. So that leads me to conclusion. Analog devices, we provide products and solutions for single pair Ethernet, and those solutions include the 10-base T1L, and we have products, we have PHY, we have Mach-PHY with small level of integration, we have 2-port switch for single pair Ethernet, and also we have these, as was the main topic of the presentation today, we have also the PSC PD controllers for the plug and play single power over Ethernet. And you can have the devices, you can get samples, you can get the evolution kits, as I said. The evolution kits come with software that you can easily play with the resistors on the part and all the features, and build your own solutions for factory and buildings. So that is from me. And if you have any questions, I'm aware of the time that we run just on time. But if you do have questions, please feel free to contact me directly or through the organizers of the event, and we will follow up. Thank you.